everyone, so we are here to discuss about Pascal's Triangle. So to start, let us define Pascal's Triangle. So Pascal's Triangle is a triangular array of numbers in which the ends of the rows are 1 and each of the others is the sum of the two nearest numbers above it. So this drawn right here is an example of a Pascal's Triangle. So the first diagonal consists of ones, which was mentioned earlier as the endpoints of each rows. The second diagonal consists of counting numbers from 1. The third diagonal consists of triangular numbers, which corresponds to the number of dots needed to form a triangle out of 1 dot, 3 dots, 6 dots, and so on. Then the fourth diagonal consists of tetrahedral numbers. Tetrahedral numbers corresponds to the number of spherical objects that are required to form a four-face figure, or specifically a triangular pyramid. So the Pascal's triangle basically has many identities, such as when the whole triangle is cut in half, it is identically similar to the other half. So another ability is that each time you go down the Pascal's triangle, it increases the powers of 2. So as you can see, the sums 1, the first row is 1, so 1. 1 plus 1 is equal to 2. 1 plus 2 plus 1 is equal to 4. 1 plus 3 plus 3 plus 1 is equal to 8. And next is equal to 16, and so on. As you can see, for every row you descend in the Pascal's triangle, you increase or double the powers of 2. So this is 2 raised to 1, 2 squared, 2 cubed, and 2 raised to 4, and so on. So the next identity of the Pascal's triangle is the exponents of 11. So each row of the Pascal's triangle corresponds to each power of exponents of 11. So you can see here 1, which is 11 raised to 0, 11, which is 11 raised to 1, 121, which is 11 squared, 1331, which is 11 cubed, and so on. But after 11 raised to 5, there seems to be a trouble with 1, 5, 10, 10, 5, 1. But it still follows the sequence because we just add these numbers, and then we can continue the sequence, which is 1, 6, 1, 0, 5, 1, which is equal to 11 raised to 5. So the next identity of the Pascal's triangle is seen in the second diagonal. The numbers in the second diagonal have squares equal to the sum of the nearest numbers at the right of it and below of the two numbers. So for example, 2. The square of 2 is 4. So the number closest to 2 are 1 and 3. So 1 plus 3 is equal to 4, which proves that the square of the second diagonal is equal to the sum of the nearest two numbers below and at the side of it. The Pascal's triangle can also be written in the n choose k sequence, such that n taken k is equal to n factorial over k factorial over n minus k quantity factorial. So to prove it, we'll choose one of the sequences to prove it. So 3 taken 2 is equal to 3 factorial over 2 factorial over 3 minus 2 factorial. Then 3 factorial is equal to 3 times 2 factorial. That can cancel 2 factorial below and 1 factorial. So let's cancel 2 factorial. Cancel, cancel. We have 3 over 1 factorial left. So 1 factorial is just equal to 1. So 3 over 1 is just equal to 3. So from the row we chose, the number that is equal to 3 taken 2 is just equal to 3 in the sequence 1, 3, 3, 1, which proves our theory. So the Pascal's triangle can also be used in binomial expansion. So for example, expand the binomial x plus 1 quantity squared. So instead of solving for the n choose k just to find a term in the whole expansion, we can just simply use the Pascal's triangle to find the coefficient next to the terms. So for example, x plus 1 quantity squared. So 1 times x squared plus 2 times x plus 1 times 1. And for the next, x plus 1 quantity cube. So instead of solving for the n choose k, you can just base from here the 1 x cubed, 3 x squared, 3 x 1. And for the final test, x plus 1 quantity raised to 4. So 1 times x raised to 4, 4 times x cubed, 6 times x squared, 4 times x, and finally 1 times 1. Therefore, it proves the statement that Pascal's triangle can also be used to easily solve for the binomial expansion. And that's all for today. Thank you for listening, and good luck. So the Pascal's triangle is basically so the next identity of the Pascal's triangle is the squares. So as you can see, the second diagonal we can see
Ako si Pascal, si Obras, si Black, si Luna, si